Thanks for downloading the InOurTime podcast. For more details about InOurTime and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. Early in the 20th century, physicists were alarmed at the realisation that the smallest things in the universe don't obey the laws described by Newton's theory of gravity. Ripe apples fall from trees, and the moon orbits the Earth in thrall to its gravitational pull, and Newton had been God. But there's no such force of gravity at work in the world of very small things. It seems there's one set of rules for the realm of everyday objects, and a very different set of laws for the quantum world, where tiny particles actually form the building blocks of all those larger things. It doesn't appear to make sense. Physicists decided there must be another theory, a much larger theory, that unites, incorporates and finally makes sense of these divided realms, and this has been the holy grail of physics ever since. Last year we explored string theory on this programme, but one of my guests today is researching what he believes is a much stronger contender for the title of Theory of Everything. He's Lee Smolin, author of 3 Roads to Quantum Gravity, and Professor of Physics at the Centre for Gravitational Physics and Geometry at Pennsylvania State University. Also with us is John Gribbin, Visiting Fellow in Astronomy at Sussex University, and Dr. Jana Levin, Advanced Fellow in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. John Gribbin, quantum theory brought us computers, genetic engineering, lasers. It's a huge achievement in science. Can you explain why Niels Bohr, one of its pioneers, said, quote, "Anyone who's not shocked by quantum physics has not understood it"? What does he mean by that?
I think the key thing that he was worried about was a business of that's called quantum jumping, when systems change from one state to another without passing through any in-between state. And the classic analogy we have is when you think of an atom, what we learn at school is an atom has a central nucleus. When we think of electrons going round it like planets going round the sun, which sounds nice and cosy, but then you find that electrons can jump from one part of the atom to another, as if Mars disappeared from its orbit and reappeared in the Earth's orbit, literally instantaneously, with nothing happening in between. And this runs completely counter to the ideas of Newton that came earlier. And at the same time, what was puzzling was what you mentioned, that physics seemed to have split in two at the beginning of the 20th century. Instead of one set of laws to explain everything, you had the general theory of relativity, Einstein's description of gravity and the universe at large, and quantum theory explaining the world of the very small, and at that time seemingly no overlap between them. So it was truly shocking to people brought up on classical physics.
I'm told, or I read, that at the heart of quantum theory is Heisenberg's uncertainty principle, which says, very, very simply, that you cannot know both the momentum and the position of any subatomic particle at the same time. Why is it impossible to measure that simultaneously, and why is that important?
Well, it's not just that it's impossible to measure. This is the big thing to get hold of. It's that the quantum entity, I don't like to use the word particle, the quantum entity doesn't itself know both where it is and where it's going at the same time.
You're going to have to just describe...
The uncertainty is not a problem with our measuring apparatus.
Yeah.
A lot of people think it is. They think if you try to measure the position of an electron, it's like trying to sort of squeeze it in your fingers and it'll pop out and fly off in a different direction, so you don't know where it's going. And if you try to measure where it's going, somehow that disturbs its position, so it's in a different place. But it's not. What Heisenberg told us is that things like electrons don't have a precise position and a precise direction, which is what momentum is, at the same time. So there's an inbuilt uncertainty in the quantum world, and that, again, is very different from what Newton thought.
Can you add your comments on that, Lee Smolin? Can you just talk about that uncertainty there and why it is so worrying? Why it was so worrying to people when they discovered it?
It's still worrying, and I think that we don't understand quantum mechanics. Quantum mechanics is a provisional theory. It works very well. If your impression is that it doesn't make sense, that's because it doesn't make sense. And I think the question you were talking about the electron jumping from place to place, is a question because it's a provisional theory that blends a classical view where space is continuous and you see things moving continuously, and some information about the quantum world where things come in discrete bits of information can either be in one place or another. But quantum mechanics is like trying to rap to classical music. It's inherently contradictory, and what we have to do now is deepen it and understand it.
When you're dealing with something that doesn't make sense, you said calmly, well, it doesn't make sense. What sort of sense does it not make that leads you to keep on trying to make sense of it?
Well, it is a mathematical formalism which illustrates the principles that you've been talking about, uncertainty, discreteness, and we can use this in order to make predictions. For example, that the energy levels of an atom do come in discrete units. An atom can have only one energy or another energy and not energies in between. So it's this amazing thing, and it's a lesson. It's a very good intellectual lesson for anybody to realize that there's something that you can use but not understand. A bit like most of us in a computer or radio or something.
But this is the point, isn't it? I mean, yeah. It's not that it's weird. I mean, if it was just weird, people would ignore it. But it makes predictions that apply in the real world. This kind of jumping that Lee was talking about is how a laser works. You know, we've all got lasers in our hi-fi systems these days. The only way we can make them is to use these weird rules of quantum mechanics. So it has practical applications. It makes predictions you can test and use in engineering. But it doesn't make sense, and that's the problem. It's the combination of being useful in practical terms and not making sense in scientific terms.
Jana, can you come in on this and add your comment to what's been said?
Well, yeah, I really do think that that's the crux of it, is that it is predictive. Not only is it predictive, but we can calculate things to unprecedented accuracy. We can predict things in particle accelerators with an accuracy that really exceeds anything we had done before. So that is why we're forced to use a theory, even though philosophically we don't understand it. And it is, in a way, kind of like using your stereo. Even if you don't understand how it works, you can still use it. And I think there's a big difference between that and something like relativity. When Einstein came up with relativity, it was counterintuitive, it was difficult, but it's logically consistent. There isn't any point which you would say, those are two mutually exclusive propositions that I cannot simultaneously hold in my mind. In that sense, relativity is understandable. Whereas quantum mechanics seems to say two logically opposing ideas have to be held at the same moment.
That's what I was going to come on to next. In the quantum world, Lee Snowden, there's an uncertain relationship of particles to waves. Whether something's a particle or a wave seems to depend, you'll correct me obviously, on whether it's being observed or not. Can you unravel that?
Well, more interestingly, it depends on how it's being observed. The difference, the simplest way to say the difference between working in the quantum world, is so far as we do, and the ordinary world, is that what we think of as the properties of things in the quantum world, for example, whether it's a wave or a particle, seems to depend on what questions we ask. And it also seems, very importantly, to work with the quantum world, we have to be self-conscious about what we physically do to ask a question of an atom or an elementary particle. That is, we can't imagine abstractly that our own existence, our activities, our measuring instruments are not there, and think about the world as if we weren't there. It seems necessary to put our own actions and our own choices about what we choose to investigate inside the science, so that whether an electron is a wave or is a particle, or better, whether it behaves in ways that make us think of a wave or behave in ways that make us think of a particle, depends on what circumstances we put it into.
Can you give us some idea of the essentiality of this particle-wave duality to the new theories?
Well, let me say where it leaves us, because I think it leaves us with two very different options. And one option is a kind of mysticism to say, the problem is with our style of thinking, with our understanding, and we should go off and invent a new philosophy to encompass this, or a new form of logic. And that's what many people have tried to do. The other response is to say, well, this just doesn't make sense, and there must be something left out. There must be some part of the phenomena which is unanalyzed, which we're not thinking about properly. And when one takes that point of view, one is led to realize that the unanalyzed part has something to do with space and with time. We're thinking about these experiments, but we're treating space and time as we always have. And the hope is that by bringing space and time into the picture and trying to think about what space and time really are, we can find a way of understanding this phenomenon which makes perfect sense to us.
There's a lot of resistance to the randomness of quantum theory, as I understand it, John Gribbin. And Einstein famously said, God does not play dice. Then we have the Schrödinger's cat, which you've written about and so on. Can you say where that, because that can give laypersons like myself some kind of grip on it. Can you just briefly fit that into what's been said?
Well, this can be seen as an example of this randomness, this probabilistic chance business in quantum physics that Einstein hated, and Schrödinger hated it as well, although he was one of the pioneers of the subject. And he invented this so-called paradox, it's not really a paradox, to highlight the weirdness of the quantum world. And his idea basically was that you could imagine a situation in which, as he put it, a cat is locked in a steel chamber with a radioactive device that has a chance of decaying in accordance with the probabilistic rules. So there's an exactly 50-50 chance that the atom has or hasn't decayed. And if it does decay, it triggers something which kills the cat. Now, the strict interpretation of the conventional view of quantum physics is that until somebody measures what's going on, which means until you look in the box, the whole system, including the cat, doesn't decide whether the atom has decayed or not, and therefore whether the cat is dead or alive. So Schrödinger said, you have this half-dead, half-alive cat, therefore quantum physics is ridiculous. And for 60 years or so, people have used this as an example and found ways to say why it's not a paradox and why it's not a puzzle. And there are there are many different interpretations of what's going on, but the fact that there are many interpretations is a sign, as Lee says, that we haven't actually got to the fundamental truth.
I'm very sure that in 100 years, much of these different interpretations of quantum theory and much of what we're talking about will be understandable only to historians of science and not to the scientists of 100 years from now who will have something that makes sense to talk about.
Also, on macroscopic scales, you do expect quantum mechanics to somehow reduce to common experience. We don't experience a state of simultaneously being here and not here, sitting on a chair and not sitting on a chair. And so there is a difficulty, I think, that people have tried to address in going from quantum mechanics to macroscopic physics, and how that transition could occur, which is a rich area also of research, but an important area because it says how there must be a limit in which common sense does hold.
John Gribbin, let's move on now to this, to trying to look at the idea whether theories can be unified, which has been, as I said in the introduction, in a sense, the Holy Grail. Do you believe that there is a possibility of a unified physics looming? And if so, what are the... obviously, Lee Smolin's book is about this, but I'll come to him in a second. But can you give us the background of that?
Well, the people, as I say, essentially for 100 years now, have been trying to put the pieces back together to find a way to make quantum physics and relativity theory, which is the theory of gravity, work together or fit together in some way. And there was very little progress for a long time, up until about the 1980s, I guess, and people like Einstein tried and failed. But there is certainly a lot of progress being made now. I'm not as optimistic as Lee. I mean, Lee sometimes gives the impression that the answer is going to emerge next week. But perhaps within 10 or 20 years, I think we might have something that makes as much sense as quantum physics did 100 years ago. And then you'd have a generation of people to put the pieces together properly. What you need is a theory that incorporates both gravity and quantum mechanics. And one way of thinking of that, the way I like to think about it, is that it's a quantum theory of gravity, which is very much Lee's area. And the difference between relativity theory and quantum physics is that relativity theory makes sense in the terms of everyday logic. It's a continuous theory. It's smooth. It says that space and time are smooth and just like we experience the surface of this table in everyday life. And quantum theory tells us that things are grainy on a very small scale. And it must be true that space and time are also grainy on a very small scale. And that's the problem, is finding out how it's grainy.
Before we turn to Lee, because this is the area which as you say, he is working most ferociously. Can we just mention string theory? Because on this programme, Brian Greene last year talked about that might unite the seemingly contradictory realms of physics. How do you imagine string theory, and what importance do you give to it?
Well, if I could just draw one distinction, which I drew out of Lee a couple days ago, which is that string theory is trying to be a theory of everything. It's trying to unify all of the fundamental forces into one theory. What Lee's doing is slightly different, and that's, I think, maybe why they might be different pieces to the same puzzle. What Lee's trying to do is quantize gravity. He's not necessarily trying to unify gravity with the other forces, although I'm sure he'd like to do that eventually. All good things in order. But in the meantime, he's just trying to make gravity a discrete theory. And so that's to be distinguished from string theory, which is trying to unify all the forces together. So I see them as slightly different tasks. And I think that the differences are important in the sense that string theory still has an element of the continuous in it. And
what is that? Can you unravel that a bit, please?
Sure. So string theory...
Bad word for string.
String theory suggests that instead of being grainy as individual particles, when you look at these individual grains, you will realize that they are loops of string, and that each string can vibrate. And as it vibrates, just like you would play different notes on a musical instrument, it will give rise to different particles. So the different particles are analogous to the notes. And in that way, it can unify all of fundamental physics by saying the electron and the quark, these are really different notes played on a fundamental string. So it's pulled them all together to one fundamental element. But in a sense, it still has a continuous in it, in that it assumes a continuous background of space-time. And the string itself looks continuous, is a continuous loop of something.
And we're talking about, we're talking about this as the building blocks of everything. Now, Lee Smolin, in your book, 3 Roads to Quantum Gravity, you talk about string theory, of course, but you, as it were, put your money on loop quantum gravity. I'm afraid you're on your own from now on. And as far as I'm concerned.
Well, it's not that I put my money on it. It's with some friends, particularly Carlo Rovelli, but dozens of other people, we've been involved in inventing and studying this approach. And so I have some responsibility for it. I actually believe that that is loop quantum gravity and string theory, are each quite possibly pieces of the puzzle, as John has said, and that the current task is now to put them together. And this is very much like, different people before Mount Everest was climbed attempted it from different sides. And I think that there are different communities of scientists who come to this problem, which is an enormous problem, with different perspectives, with different tools and backgrounds, and have approached it in different ways. And broadly speaking, among the different approaches, there have coalesced these two communities of coherent, more or less coherent efforts, one of which is roughly called string theory, and one of which is roughly called loop quantum gravity. And I agree with Jana's characterization. The driving idea behind string theory is to unify gravity with the other forces and with the different elementary particles, but without attacking really the question of the quantum nature or the continuous versus the discrete nature of space. What we did in loop quantum gravity was put the question of unification aside and attack directly the question of what is the quantum nature of space. And the answer we got, because we did get a clear and clean answer, is that if you unify the principles of quantum theory and relativity, predictions emerge, and the predictions are that at a certain scale, which is called the Planck scale, it's very, very small, but at this scale, space looks no longer continuous, but it gets broken up into little irreducible units, much like matter gets broken up into little atoms. And this graininess or atomic structure of space is the main prediction, and indeed it is a prediction to be tested by experiment, and we believe actually is in the process now of being tested by experiment.
And so where does that take you with unifying it with the gravity from theory of relativity? How does that bring it together?
Well, it's a consequence of insisting that the basic principles of quantum theory and the basic principles of relativity both be true. And what we did was just very stubbornly insist that both sets of principles be true, and then find consequences of them. And the shock for me, it was very much a shock, was that we succeeded. I thought that by stubbornly insisting on both being true, we would discover that one or the other had to be false. Well,
is it a consequence of what you've discovered? Well, and I talk to John and then come back to you. Is that the shape of the universe, this three-dimensional universe that we see, is that changed as a consequence of this? I mean, people listening and following what you've been very clear about saying want to ask, so if that is true, are we looking at it the wrong way? Will our imaginations turn and look at this thing in a different way as the consequences of what you've done? Does it exist in a way which will be revealed to us, not in any magical way, but through knowledge, these sort of things?
Oh, I certainly hope so, yeah. So, as you know, one of the things I've been interested in is the shape of the universe, whether the universe is finite or infinite, and whether there are three dimensions or more dimensions. And certainly string theory, I wouldn't say it makes a prediction yet, because it's not a complete theory, but it does require often in different formulations that there be extra dimensions and that the extra dimensions have a specific shape, so that we don't live in a three-dimensional universe, but we can live in a universe with 10 or 26 dimensions, or it depends on the specific incarnation of the theory. And so if it says something about the compact dimensions, the hope is that, or these small extra dimensions, I say they're compact because the idea is that they're so small we can't notice them. We're so small we can't fit our hands in them in some sense, so we're not aware that they exist. It's kind of like living in a straw, and you're aware of the long length of the straw, but not the small wound-up dimensions. But the hope is that when string theory is complete, and maybe also loop quantum gravity, I'm not sure, that it will say something about the large dimensions also. And so it would be one of those ironies that by looking at the largest property of the entire cosmos, that we could understand something about its smallest constituents.
John Gribben.
I think the exciting thing for me in all of this is that there seems to be some suggestion that there are reasons why there should be three dimensions of space and one of time, even though there are, at the level you're talking about, 26 or whatever it is dimensions altogether. And that understanding the other way round from what you said look at the big universe to understand the small. To me, I hope that understanding why things have rolled up in this way to leave just three dimensions behind would explain why there was an event like the Big Bang,
yeah,
which
I absolutely agree.
Which Lee, rather nicely calls the Big Freeze, because the universe was hotter and in the Big Bang, and then it got cold, which is a nice way of thinking about it. And that something happened. Something happened in terms of the energy, what was going on long ago, and that made the universe what it is today. And it raises other questions which are addressed in Lee's book. Is that what went before, which is the thing that I've been asked for, years and years and years, and I've always said, oh, well, that's beyond the knowledge of cosmology and so on. And people are now starting to ask that question. Was the Big Bang, the Big Freeze, whatever you want to call it, a unique event, the beginning of everything, or was it a change from some pre-existing state, which is very exciting and suggests that there might be something much bigger than our universe that we know about, and that we're some kind of bubble embedded in that, in which, for reasons which Jana will no doubt discover in a few years' time, three dimensions have become important, and the others have all got rolled up into tiny strings.
Jana, how confident are you that physics will solve this problem?
It's a subtle question. I'm sure that Lee's right. We will have one day a quantum theory of gravity, and I think we'll either unify or understand why it can't be unified, and something else will take its place. There's definitely something's going to happen. Something big is going to happen. But whether or not that's going to be the end of theoretical physics, that's something that I'm more skeptical about. And I think there is this attitude that we'll solve it and that we'll all become applied physicists after that. I don't think that's so likely. But I do think that something has to give. We can't continue in this state of quantum mechanics, gravity, all the forces not somehow speaking to each other in a more eloquent way.
John Gribben.
I think it's important, though, that we shouldn't sort of run away with the idea that all the old physics is wrong. I mean, people said 100 years ago, when Einstein's theory was proved right, they said, the newspaper headline said Newton overthrown and things like that, which is total rubbish. I mean, you still use Newtonian physics if you want to build a rocket to go to the moon. And when we have a unified theory of gravity and quantum physics, that won't mean that we stop using the general theory to describe the universe at large, or quantum theory if we're designing lasers or whatever it might be.
When, Lisa, let's assume that you're optimism. You declare yourself to be an optimist in the book. Let's be optimism. Let's hope your optimism is justified.
Face reality.
Yeah, absolutely.
Yes.
How big an impact do you think such a discovery, a unified theory, would make? I mean, on the scale of things, is it as big an impact as the theory of relativity? I mean, how big an impact is it going to have on not only on the thinking in cosmology and physics, but as it were on the rest of us and what happens?
Of course, we don't know, but if history is any guide, huge. There will be a huge impact. One is, as I was saying, and there's more to say about this than we have time, but the transition to a view of the universe in which everything is dynamical. There's nothing fixed. It's a system of relations which continually evolves in time, and we're a part of it, is a very important part of what's happening in 20th century, in 20th century science, all across the board. And I think that this is already having an impact in art, in thinking about social theory. Although there's much work to be done, I have the sense that the turning the corner and laying on the table the basic principles of a quantum theory of gravity, the basic shape of the ideas, has happened. There's an idea called the holographic principle we haven't discussed, but which changes completely this issue about observation and how it affects the world in quantum theory. There are the structures that come out of string theory, these predictions of discrete space from loop quantum gravity. I personally think we're kind of in the mopping up phase where we have what we need on the table and we're just putting it together.
Joanna, do you want to go another?
There's so many things. Well, first of all, I think Lee said it best when he said, if history is any guide. I think that's true. If history is any guide, there's going to be huge ramifications, ones that we simply can't foresee. And you have to remember, Einstein himself rejected some of his most outrageous predictions. He rejected black holes and the Big Bang for a long time before he finally gave way and accepted them. So there are outrageous things that can come out of a theory that we can't foresee. And maybe Lee's right, we're in the mopping up phase, although I'm more skeptical. I think we have a lot more work to be done, but if we are in the mopping up phase, maybe we're all too close to it to see it. Maybe there are extraordinary predictions that we still are ourselves being too rigid. We like to see ourselves as visionary and very flexible and very adaptable to new ideas, but I think there's a good chance that we're less so than we hope, and that things are right in front of us. We don't yet know. I know Lee's shaking his head yes, so that's good.
There's a sense in which we can almost calculate what Newton's ideas brought to the general world, and Faraday's did, and they brought this, and Einstein's did. What will this theory bring, do you predict, John Gribbin?
Well, you mentioned Faraday, so it's an obvious opportunity to trot out the famous quote. When Faraday was asked what use electricity was by the Prime Minister of the time, he replied, "I don't know, but I'm sure one day you'll tax it." And I think we're probably in the same situation here. If there is a quantum theory of gravity or a unified theory, given time, it'll be actually used for practical purposes. And when those practical purposes come to fruition, they'll be taxed, I'm sure.
Thank you very much, Lisa Merlin, John Gribbin and John Levin, and thank you very much for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.